This topic covers column hydraulic analysis for rating and troubleshooting. In the previous topic, we discussed the interactive sizing mode and how it works. In summary, interactive sizing mode means that the geometry dimensions, such as diameter, downcomer widths, wear lengths, and hydraulic plots, will automatically update based on the vapor and liquid flow profile and specified geometry. In comparison, the rating mode of column hydraulic analysis means that all flow-dependent geometry is fixed and will not be updated when operating conditions change. Users need to specify these dimensions. In industry, column rating studies are needed for many scenarios. For example, when evaluating the feasibility of increasing product throughput in a column or changing a column feedstock, rating studies are important to give guidance. To use the rating mode in column analysis, detailed information of column internals is required, such as downcomer and tray geometry details. These details can be provided from either the interactive sizing mode or as user input. In the section sheet of the column analysis interface, the rating mode can be enabled by switching the mode from rating to sizing. Users can determine how the pressure drop calculation results will interact with column performance in the flowsheet by choosing update options like Don't Update Pressure Drop, Update Pressure Drop from Top Stage, or Update Pressure Drop from Bottom Stage. In rating mode, users will specify the column's section diameter and other tray or packing details. Alternatively, the initial sizing calculations can be used as a basis. After running the model, column analysis will calculate hydraulic results, such as flooding approach, downcomer backup, and pressure drop. When in rating mode, input values cannot be recovered if they are deleted. However, in sizing mode, the values can be cleared to default by highlighting the size-dependent geometry value and pressing the delete key. During the sizing and rating process, some common errors and warnings may pop up in the column hydraulic plot, such as jet flood, downcomer exit velocity is greater than maximum allowed, wear loading error, and weeping. Those errors and warning messages indicate that the column isn't working in proper operating condition. In the next few slides, we'll introduce the general guideline to troubleshoot some typical problems. Jet flood is a common problem. There are a few strategies to troubleshoot the column if you see jet flood. From a geometry perspective, by increasing the diameter of the column or increasing the number of passes, the gas velocity can be reduced to avoid the jet flood. Typical design practices omit 3-pass trays due to their asymmetry. Furthermore, they tend to operate unreliably in the industry. Users can consider these options in the designing or plant revamp phases. However, if the column is under operation, users can try to change the operating specs. The potential solutions include increasing condenser pressure, pre-cool feed, reduce feed flow, reduce boil-up, or reduce reflux. However, the success of implementing these operational changes is dependent on the system and volume flow profile for the column you're working with. To troubleshoot weeping, users can decrease the column diameter in a design phase or block off sieve holes or valves during a turnaround in operation. The actions can increase the vapor velocity in the column, but the tray performance may become downcomer limited. When the downcomer exit velocity exceeds the maximum downcomer backup limit, one possible remedy in the design phase is to increase tray spacing, which may reduce downcomer exit velocity, but this increases the overall column height. Another possible remedy is to increase the wear height and downcomer clearance while potentially facing downcomer face choke flood. If the column is in operation, retray considerations might happen during a revamp. Switching to a packed column is also another option to column designers if very low pressure drops are required or liquid rates are low. Typically, structured packing achieves a low pressure drop and a high efficiency. The other typical reason for switching to a packed column is the capital cost. If the calculated column diameter is under 2 feet, the high fabrication cost of small trays might suggest that packing is a suitable alternative. In the first demo, we will utilize the rating capabilities of column analysis to determine the upper limit for the turn-up capacity of an HCl column. The detailed information of the HCl column internals is provided from sizing mode in the previous topic. Let's go to column internals to change the mode from interactive sizing to rating for all three sections. For this evaluation, we will update the column pressure drop from top stage based on the tray hydraulics. Now we will investigate the effect of column throughput on the percent jet flood and percent downcomer backup to determine the upper limit for turn-up capacity. We will vary the feed rate using a sensitivity analysis by varying the multiplication factor of a multiplier block. Add a multiplier block from the Manipulators tab of the Model palette and connect the required streams. Enter a multiplication factor of 1 on the multiplier block specifications sheet. Return to the column specification sheet to reattach the feed to stage 35. Now let's set up a new sensitivity analysis. Use the multiplication factor as a variable to manipulate the feed rate. We need to define variables such as percent jet flood and percent downcomer backup in the sensitivity analysis to understand the capacity limit. Navigate to the results form of the top section CS-1. Copy the value of maximum percent jet flood and paste it into the define sheet. Rename it to Flood 1. Repeat for the maximum percent downcomer backup and rename it to DCBA 1. Repeat for the other two column sections. On the Tabulate sheet, click the Fill Variables button. Run the simulation and plot the results. The plot shows that even at 150% turn-up, the jet flood limit 80% is not approached. However, the downcomer backup limit 65% is exceeded. At 116% turn-up, the downcomer backup limit is approached. Since we need to satisfy both constraints, the maximum turn-up capacity is 116%. In the next demo, we'll utilize the rating capabilities of column analysis to troubleshoot a column in the methylamines production process that is showing operational issues. Let's start by seeing where the trouble is with the base case. Navigating to the C400 column, double-click the column and navigate to the hydraulic plots to see the current performance. The performance issue seems to occur right around the feed stage. We can see that the column is flooding. Because this occurs around the feed stage, one idea is to reduce the vapor fraction of the feed stream. Other alternatives may be to reduce the boil-up ratio or reduce the column operating pressure. Use the flowsheet Modify ribbon in Aspen Plus to make the vapor fraction visible in the flowsheet. Note that the feed is going to C400 is entirely vapor. Insert a heater block into the stream, MMA-DMA, and connect the required streams. Set the pressure to 100.08 psia and the vapor fraction to 1 in the heater specs. These values come from previous MMA-DMA stream results. Return to the column specifications to set the feed stage to stage 50. Run Aspen Plus to converge the flowsheet. Now reduce the vapor fraction from 1 to 0.6 and run Aspen Plus. If you compare the temperature of the original feed stream MMA-DMA with the new feed stream S1, there is 1.5 Fahrenheit reduction in feed temperature, which an operator can potentially control in the plant. Now open the hydraulic plots for this C400 column. Notice that nowhere in the tower is the jet flood boundary violated.